Welcome back to our ARSET training series, Introduction to Thermal Remote Sensing and Applications in Urban Heat Island Mapping. Today is part 2 of our training series, Applications in Urban Heat Island Mapping. My name is Savannah Cooley. I'm a researcher at NASA Ames Research Center with the Bay Area Environmental Research Institute in Mountain View, California, and I'm a trainer with the ARSET Ecological Conservation Team. We have 2 instructors for part 2, myself and our guest instructor, Glyn Hulley, who is a research scientist in the Earth Science section of NASA Jet Propulsion Laboratory. For part 2, we have 2 objectives. First, participants will be able to filter and visualize ECOSTRESS land surface temperature data using provided R-based data processing workflows. Second, participants will be able to downscale native 70-meter ECOSTRESS LST data to a fine 10-meter spatial resolution using a random forest machine learning model implemented on an interactive Google Earth Engine interface to analyze neighborhood-level urban heat patterns. If you have questions during today's training, you can put them in the Q&A box within WebEx at any time. We encourage you to put your questions into the Q&A chat as they arise. The earlier you share your questions in the chat, the more likely it is that we will be able to respond to them in real time during the Q&A session. If there are questions we do not have time to address during the live Q&A session, we will make sure to collect these and post the written answers to the training page within a week after the training. In other words, we will try to address as many questions as we can today. All of these questions and answers will be posted along with the additional questions and written answers to the training page within a week after the training. Before we delve into our next section, let's review some of what we learned in part 1. Remember, satellite sensors measure radiance and convert it to brightness temperature, which is defined as the temperature a perfect black body would have to be to emit the radiance we observe. The problem is that real surfaces aren't perfect black bodies. They have emissivities that are less than 1. If we assume everything has an emissivity of 1, we'll systematically underestimate surface temperature. Let's do a knowledge check with a numerical example. What is the radiometric temperature of a sandy desert surface with emissivity equal to 0.9 and kinetic temperature equal to 320 Kelvin? Take a minute or two to work this out on your own before I walk through the answer. With a sandy desert surface having an emissivity of 0.9 and a kinetic temperature at 320 Kelvin, we can calculate the radiometric temperature as follows. We would raise the emissivity to the power of 0.5, as shown here, multiply that by 320 Kelvin, and then the result is 311.7 Kelvin, which corresponds to answer D here in the set of answers. This implies that there is about an 8 Kelvin underestimate of the surface temperature if emissivity is ignored. The key takeaway is that the lower the emissivity, the larger the gap between what a sensor measures and the surface's true temperature. This is why accurate emissivity is so important, and why we will spend time delving into the topic in this training. With that, I will turn it over to Glyn to tell us about ECOSTRESS land surface temperature data.
Okay, good morning, everyone. My name is Glyn Hulley. I'm a research scientist at NASA's Jet Propulsion Lab. We have spent the past 20 years or so specializing in thermal infrared, remote sensing, and also spectroscopy applications and science. Today I'll be walking through how we sharpen, or also sometimes called downscale, ECOSTRESS land surface temperature from its native 70-meter resolution down to a 10-meter resolution using a random forest machine learning approach, and we'll be doing this within Google Earth Engine API. This technique opens up a whole new range of applications for thermal remote sensing, specifically in urban settings. And by the end of the session, you should be able to run the pipeline by yourselves and create your own high-resolution maps over any city in the US using data since 2018 when ECOSTRESS first started taking observations. Okay, so I'll be first going over some introduction on ECOSTRESS, followed by urban heat islands, and then we'll go into some of the theory of the downscaling. So ECOSTRESS was launched in 2018. It's docked on the Japanese experimental module on the International Space Station, and it's been delivering thermal infrared observations since about August of 2018. We're currently funded through about 2029, which is really great considering that the initial mission was only supposed to last about 1 year. But we've been extended due to the credible success that we've had in science and applications from the data from the instrument. The native pixel resolution size is 70 by 70 meter resolution, and we acquire data on average 3 days over most parts of the US and also the globe. And also one unique thing about ECOSTRESS, and that we'll cover over the next few slides, is that we can take these observations over the entire diurnal cycle. We also have 5 spectral bands in the thermal infrared, which is also unique amongst current spaceborne thermal instruments. So moving on to some of the actual characteristics of the instrument, what I've shown here is an actual example snapshot of what we call a scene or a granule that we observe from the space station. Each of these snapshots, think of a camera snapshot, is around 400 by 400 kilometers wide, so a really wide snapshot. And within that, we have 70-meter resolution pixels, which is about the size of a small football field. And this is currently the highest resolution thermal data from space. Now, with the precessing orbit of the ISS, meaning it doesn't come over the same place on Earth every single day, like Landsat and ASTA, for example, this image shows the number of observations we get over a 3-month period over the diurnal cycle, which is shown in UTC time on the left y-axis here. So you can see that ECOSTRESS in blue captures a lot more observations than both Landsat 8 and 9, and also throughout the diurnal cycle, whereas Landsat only captures at a single time around the early morning overpass every day. The 5 thermal bands, which you've probably learned about in Savannah's tutorials, are located between 8 and 12 micron range. This is the classic long-wave thermal infrared region where we can retrieve the surface temperature from. And these 5 bands, typically the more bands we have in this region, the more accurately we can derive the surface temperature and also the spectral emissivity from the thermal infrared measurement. So just some quick latest news from ECOSTRESS. Currently, the Collection 2 products are available from NASA, but we are delivering Collection 3 science products. So specifically, the Level 2 land surface temperature product has an imminent release at the LPDAC. And there's a number of improvements in that product. Specifically, we have a new sea surface temperature algorithm and a lot of improvements to the data quality and also cloud masking. Also very exciting for us this year is that, and I'll be showing you, of course, the demo in Google Earth Engine, is that the entire ECOSTRESS land surface temperature archive has now been ingested into Google Earth Engine over the entire continental US. So this is fantastic news for us and opens up a lot of data and science and applications that we can use with other data within Google Earth Engine. We have more than 1,000 peer-reviewed publications so far, and since early this year, we've acquired more than 606,000 of these 400 by 400 kilometer snapshots I showed you earlier. We also have a new applications page referenced here. You can see that we support a diverse discipline of different science applications. The one, of course, we'll be focusing on today is urban heat and urban resilience. So what makes ECOSTRESS unique? As I mentioned earlier, most thermal sensors in space have a sun-synchronous orbit, meaning that they cross overhead in the mid-morning hours, in this case for Landsat and ARSET, it's around 10 or 11 a.m. And you can see in this Los Angeles temperature profile that I've shown that the morning overpass, which is this white line going across the screen, typically misses the warmest times of the day and the hottest times of day in the peak afternoon hours. And this is critical for urban heat mapping because you'll miss the maximum temperatures during a typical urban heat extreme event. If we look at ECOSTRESS, we sample across the entire full diurnal cycle and seasonal cycle, which is exactly what makes it uniquely valuable for heat stress and urban applications. So then moving on to urban heat islands, I'll give some background on urban heat islands, what we've done so far with ECOSTRESS, and then we'll move on to the fun part, which is the downscaling. So why does this matter to us? Well, heat waves are, a lot of people don't realize this, are the single biggest weather-related killer in the United States. They more than double that of floods, tornadoes, and hurricanes combined even. So as you can see on the chart on the left, this is the NOAA National Hazard Statistics chart. Heat fatalities are running by roughly 200 deaths per year over the last decade. And a lot of people don't realize this because you can call them the silent killers. They don't cause as much physical destruction as other natural disasters, and so you don't hear about them as much. And the downstream impacts go well beyond just mortality. For example, there's increased risk of heat stroke or hypothermia. These are the most common ER visits. And a lot of these are typically make a lot of sense. Increased electrical demand from the use of AC, higher wildfire risk, especially in the Southern California region in the later parts of the year when we have Santa Ana events. And then, of course, degraded air quality due to the increase in near-surface ozone. And these health effects also exacerbate, for example, other underlying conditions like cardiovascular and also mental health and cognitive function. Over the last few years, we've spent a lot of time with a lot of very enthusiastic summer students at JPL, where we've now mapped most of the extreme heat events with ECOSTRESS in cities across the world. So what you're seeing here are snapshots from these images in European and US cities from Prague, Toulouse, all the way to Birmingham, Milan. And sharp and ECOSTRESS data have been featured in both BBC articles, and also the European Space Agency typically features an article every year on how cities can adapt to heat waves, particularly during the nighttime. And it's also increasing up by city planners, public health teams worldwide, and a lot of the media within the US. So I'll go through some examples and why ECOSTRESS is unique in its ability to capture urban heat islands and urban heat in general. So this is a case study over what is called the Cheribus heat wave in July 2023. It broke all kinds of records across Europe in terms of heat. This is over Athens in Greece. On the left, we have a daytime ECOSTRESS scene, and on the right is a nighttime ECOSTRESS scene at 11 p.m. And so in the daytime scene, you can see an actual urban daytime cool island effect, which most people don't realize is that during the daytime in certain cities, the urban area can actually be cooler than the surrounding agricultural area that is driven by very hot, bare rural soils during the summertime, where we have generally less healthy vegetation. But at nighttime, that picture flips. So the city retains its heat due to high thermal heat capacity during the day, and then that stays significantly warmer than the surroundings at nighttime. And it's that nighttime urban heat island that really drives up heat-related illness in cities around the world. And it's only really ECOSTRESS that can capture these type of dynamics and changes in the urban heat island. This is another fantastic example from Macy Runkle at Chapman University, who was with us last year, looking at how urban heat island intensity changes over a full 24-hour period in Delhi, India, in this case. So each circle here represents the UHI, which is the difference in the rural and urban temperature every 2 hours throughout a typical summer cycle in Delhi. So you can see that the urban heat island is at maximum during about 10 p.m. at night. And then throughout the early morning hours, it slowly diminishes as we go clockwise around the images here. And then during the daytime, you can see that that flips. So around 10 or 12 p.m., that flips to a cooling urban heat island effect. So the city is actually cooler than the surrounding dry urban rural landscape. Another real striking example here that got a ton of news media attention back in 2024 was led by Ashley Agatep, also from Chapman, another summer student of ours. In 2024, actually in 2023 as well, there was suddenly a very sharp spike in hospitalizations from people in the Phoenix area from severe contact burns. And these were mostly due to several extreme heat events that occurred over those 2 years, and actually resulted in almost 50 fatalities. For example, the gentleman here on the left actually lost his leg when he fell on the hot sidewalk walking out of a grocery store, and wasn't able to get up because every time he put his hands on the sidewalk, it would be so hot that he wouldn't be able to push himself up. And he actually lost a leg from third-degree burns as a result. So what we did here was we mapped the second-degree burn risk by downscaling ECOSTRESS temperatures down to 10-meter resolution over the city and extracted it over the sidewalks and paved areas. And then we correlated that with the time it would take to get a second-degree burn if someone came into contact with that surface. So as an example here, you can see over most of the Phoenix area, specifically in the poorer regions in Maryvale, for example, where the surfaces exceeded 150 degrees Fahrenheit. That's almost hot enough to cook an egg on the sidewalk, by the way. It would take less than 3 seconds to get a second-degree burn risk if you fell on the sidewalk or the paved area. And so this work was really popular and was featured in Scientific American, LA Times, New York Times. It even made the Nature image of the month for 2024 in August, I believe. And so it's this kind of public health communication that thermal remote sensing can directly support, especially for city health officials. So in the next part, Savannah's gonna lead you through a hands-on exercise with land surface temperature in LA County, where she's gonna step through how to visualize ECOSTRESS LST using a number of different software. We're gonna use Appears to download the data and then visualize it with QGIS and also R.
Thank you, Glenn, for that excellent foundation on urban heat islands and ECOSTRESS land surface temperature. We are now transitioning to a hands-on exercise exploring nighttime land surface temperature in Los Angeles County. Nighttime LST is a metric that is often just as critical for public health as daytime peak temperatures because sustained nighttime heat prevents physiological recovery from heat stress. By focusing on the nighttime, we can accurately quantify the thermal gap created as impervious urban surfaces slowly re-radiate trapped heat, while natural and irrigated spaces provide cooling through evapotranspiration. In this demo, we will use R to define and determine if these natural cooling benefits actually persist as a heat wave intensifies, allowing us to identify the most effective locations for thermal interventions like tree canopy investments. The two objectives for this demo are to access, filter, and visualize ECOSTRESS LST data using Appears, QGIS, and R, and also to interpret LST characteristics for assessing urban thermal resilience. The activities for this demo include the following. There are some preparation steps, including cloning the GitHub repository or just simply downloading the R script. Second would be to make sure that you have R and QGIS installed if they're not already, and then installing any required libraries that the R script lists. The script processes ECOSTRESS land surface temperature products by converting Kelvin to Celsius and applying mandatory QA and cloud masks to ensure only reliable surface temperature pixels are analyzed. The script then defines and isolates specific geographic boundaries for the Chatsworth Nature Preserve and an adjacent commercial area as an example, which allows for a direct comparison of different land covers. In particular, we will evaluate nighttime cooling dynamics by analyzing the differences in heat release between natural open spaces and impervious urban surfaces during the September 2024 Los Angeles heat wave. We will assess thermal resilience by determining if the cooling benefits of urban green spaces hold or erode as heat accumulates over multiple days of extreme temperatures. By extracting individual 70-meter pixel values into a tidy data format, the script generates mean temperatures and standard deviations to quantify the thermal behavior of each site. Finally, the analysis will produce a suite of sophisticated plots, including side-by-side LST maps, violin box plot distributions, and thermal gap bar charts to visualize how the temperature difference between green and gray spaces evolves over a 23-hour window. One thing I'd like to flag is that the nature preserve we focus on for this example comparison with the urban commercial area is in large part possible due to irrigation. So you will notice that in many of the unbuilt lands surrounding the urban area in the hills, for example, outside of Chatsworth, the temperatures aren't much lower than what we see in the urban areas. This is because although there is vegetation in those areas, there is no irrigation. So the evaporative cooling capacity is much lower relative to the managed parks and other gardens that are well irrigated. So water helps plants stay cool, and if water is limited during a heat wave, plants will close their stomata to conserve water at the cost of having a higher temperature. I won't discuss this in the demo itself, so I wanted to just state that now as something to consider when we think about temperature impacts of green spaces. With all that said, let's start the demo. One thing I'd like to note is that these data from ECOSTRESS were obtained through an appears request. And appears is the application for extracting and exploring analysis-ready samples. It's a tool that has a number of different data sets where through the extract feature, you can get specific points or areas that are also able to be bounded both spatially and temporally. So I'm going to go ahead and log in here and just show briefly the request process. There is a more in-depth instructional video for accessing ECOSTRESS data and other data sets with appears that will be linked to in this training resources page. But for the purposes of demonstrating here, I'm just going to show how we submit an appears request. So I'm going to give this request a title. And then I have an existing area of interest in Los Angeles County in California that will be the focus of this request, this data request. So I'm going to go ahead and upload that file here. I'm adding here a GeoJSON file that is defining the area of interest over LA County for which the data were requested for. And this demo will focus on one of the hottest summers on record, which was the summer of 2024. place in early September. And so the start date is going to be September 3rd, 2024. And the end date will be September 9th. The product we're interested in is ECOSTRESS land surface temperature. Land surface temperature, this is the one that we will focus on. We will also want the quality control data layer, QC, file, as well as the cloud mask. So those are the three data sets that we'll be requesting here. And the file output file format will be GeoTIFF. Optionally, we can use calendar date and time for output file names. And then I'm just going to include geographic, which is the WGS 84 EPSG 4326 coordinate reference system. With that, we'll go ahead and submit the request. A peer's request, depending on the size of the request and the amount of data that are being requested, can take some time to process, from hours to even a couple days. And so to speed things along for the purposes of this demo, I already have an existing request that I submitted ahead of this demo and have downloaded that data from the email that is sent automatically when the appears request is ready to be viewed and downloaded. The way that I will look for these data, if you're already logged in, you can click Explore. So because this was a small area and number of files, the Appears was able to process it relatively quickly. And so we have the results of this request already to download. Here are the files that are included, where we will just go ahead and download all of them. And this may take a little while, and notice that for the purposes of this demo, I'm only using 6 out of the 22 files here, which ended up being the ones that had the fewest number of clouds and kind of were the covered the most area in the study area. So again, it's okay to just use the data directly from Zenodo, but I just wanted to illustrate how those files were obtained. And the download is now complete. So this is how the data were obtained from Appears. Now we will go to QGIS and inspect the data visually. Let's start by adding a base map. I'm using the HCM GIS plugin to bring in a satellite base map. Let's zoom in to Southern California and add our data. For now, we will focus just on the land surface temperature data. We'll do the filtering with the quality control flags and the cloud mask later on. And let's go ahead and visualize symbology that shows a color ramp. Notice that the values here are in Kelvin, so we haven't yet to convert these into Celsius, which we'll do later in R. But for now, just to get a sense of where the hottest and coldest temperatures are, we can go ahead and apply this color ramp. Feel free to change if you have a different ramp that you'd like to look at. There's lots of different options here. And we'll do the same for the second day that we'll be looking at, which is September 5th. So notice that these two ECOSTRESS acquisitions from these 2 different days have some amount of spatial overlap, but are not fully spatially overlapped. And correspond to almost 24 hours difference between these 2 acquisitions. So just by visually inspecting, we can see that this area of Los Angeles County has a mix of impervious surfaces, kind of built up areas, as well as more vegetated areas and green spaces. And just through visual inspection, we can see differences in temperature in these urban areas where there are larger green spaces. So let's start by looking at the Chatsworth neighborhood in northwestern corner of LA County, about 30 miles from downtown. And we will zoom in here. What you're looking at is the Chatsworth Nature Preserve on the left, and then an adjacent commercial area, which is immediately east of the nature preserve. These 2 areas sit almost side by side, so very similar weather and both experiencing the same heat wave. The question we're asking today is whether the surface underneath makes a measurable difference in nighttime temperature and whether that difference holds up after days of sustained extreme heat. So after the first night of the heat wave on September 3rd, ECOSTRESS captured this image. And note that the naming convention here is in UTC, which in our case, we're looking at September 3rd at about 11 p.m. local time, so Pacific time. Even just at a glance, you can see cooler tones in over this nature preserve compared to the surrounding area, with the built areas showing warmer temperatures compared to the nature preserve. And then we can also be curious about the second overpass, which is captured almost exactly 24 hours later on September 4th around 10:30 p.m. local time. So let's go ahead and check that and just see. Note that there are some differences in temperature patterns here, but the overall kind of takeaway is that there seems to be a consistent difference even after another full day of the heat wave, where there are lower temperatures in this nature preserve compared to the surrounding built areas. And by this point, LA had baked through a full day of extreme heat. Burbank hit 108 degrees Fahrenheit that afternoon, So these surfaces had been absorbing solar radiation for 14 hours before the satellite passed overhead. And as I said, the general spatial patterns do look similar. The preserve still reads cooler than the commercial area, but is the magnitude of that difference the same? Has the heat accumulated enough that even the preserve can't recover overnight? That's what we're going to quantify in R. So first, we will navigate to the GitHub repository for this training, where there is a README file detailing an overview, the prerequisites, data requirements, downloading process, and a few notes on setup. We will go ahead and download the R script here. Go ahead and save this file to a location on your local computer. And open the file in RStudio. Here we have the R script loaded. A written description of the focus of the script is here, which we also discussed in the slides leading up to this. So I'm going to let participants review this on your own time. The first section here, section 1, is to load all of the libraries. Go ahead and load them. If there are any libraries here that you don't already have installed, make sure to install them. And now we will go ahead and obtain the data for this demo, which is stored on Zenodo. So make sure to update this for repo dir variable, which is where the data will be downloaded. Here I've made a folder, 2026 thermal RS urban heat demo. So that's where I am keeping the data for this demonstration. If you're following along, go ahead and update this variable to wherever you'd like to store the data. This is the link to the data set, which has all of the ECOSTRESS files. And then we will go ahead and in this portion of the script, it downloads and unzips the data as long as it's not already there in the first place. And I'll call you attention to the two files that we're focused on. One is, like I said, the first night, September 3rd, around 11:14 p.m. Pacific time. And then we have night 2, which is September 4th at 10:26 p.m. Pacific time. So let's go ahead and run this section of the script. All right, that ran successfully. Section 3 focuses on is the processing function for processing ECOSTRESS data. One important note I want to flag here, because it's a common point of confusion in ECOSTRESS workflows. If you look at the level 2 algorithm theoretical basis document, known as the ATBD, or older tutorials, you'll see a 0.02 scale factor applied before the Kelvin to Celsius conversion of the data. And that scale factor is correct, but it only applies for the native HDF5 swath product, where integer storage requires that rescaling step. What we're working with here are the GeoTIFF tiled data, which are analysis ready products from APPEARS, where the scale factor has already been applied and values are stored as float 32 in Kelvin during APPEARS processing. So we will skip the 0.02 multiplication entirely and go straight to subtracting 273.15 which is what we do to convert from Kelvin to degrees Celsius. And this is the line that applies the quality control flag, where we're only extracting bits 0 and 1. And so this is the other thing that I wanted to highlight, is just the QC masking, where the QC layer is a bit-packed integer, where multiple quality flags are encoded in different bit positions within the same value. So bits 0 and 1 carry the mandatory QA flag, where 0 means high quality and 1 means good quality. Bits 2 and 3 mean poor or cloudy. If we just wrote QC greater than 1 as a raw integer comparison, higher order bits unrelated to quality could flip us into masking pixels that are actually fine. So the modulo 4 operation here extracts only the 2 least significant bits, which is the standard bit manipulation approach for this kind of packed flag field. And finally, the cloud mask. The L2 user guide was updated in 2024 to explicitly note that in collection 2, cloud information is not propagated into the QC bit field. So that means that QC filtering alone is not sufficient to filter out all clouds. So you must apply the separate cloud mask layer. Our function here does both in sequence. So I will now run section 3 of the code. Night 1 comes back at roughly 13 to 29 degrees Celsius, and night 2 goes from about 12 to 35 degrees Celsius. That upper bound climbing from 29 to 35 already tells a story. After a full day of heat loading, the hottest urban surfaces are retaining substantially more heat by the second night. A quick note I'll say on the coordinate reference system situation. So the file name contains 11N, which refers to UTM zone 11 north, but the geotiff files themselves are stored in geographic coordinates, WGS 84 longitude and latitude. The 11N is part of the ECOSTRESS tiling grid naming convention, not the storage projection. So to avoid any CRS resolution issues, we keep everything in WGS 84, which is EPSG 4326, and we define our AOIs directly in decimal degrees. So this is our default AOI that we're looking into. If you remember what we saw, the map on QGIS, we have the latitude and longitude bounding box coordinates for the nature preserve area in Chatsworth, as well as a coordinates box around the extent of the commercial area that's adjacent to this nature preserve. So for the homework, you all will be looking at this other area of interest to do a different analysis in a different part of LA County. But for today, we're going to go ahead and so you can see this part is commented out. I'm going to go ahead and run this section 4 here. Section 5 will produce a side-by-side map comparison where we can see these 2 ECOSTRESS acquisition dates side by side with the 2 areas of interests highlighted. So I'm going to go ahead and run section 5, where you can see we're using the ggplot package for visualization. You can see that these two maps are helping us visualize the data using an identical color scale, which is intentional and important because when you're comparing two images temporally, you need the colors to mean the same temperatures in both panels. If each panel were auto-stretched to its own range, warmer night 2 pixels would look the same color as night 1 pixels, and you'd lose the ability to make a visual comparison. So the green and orange outlines mark our two study areas. Even from the map alone, you can see the preserve tends toward cooler end of the palette in both nights. What we can't see clearly from the map is the magnitude of this gap, or whether it changed between nights. That's what the next two figures will quantify. So in section 6 here of the code, we are pulling every valid 70-meter pixel that falls within each bounding box for each night. Each row in the resulting table is 1 pixel, so one actual satellite measurement. And this gives us the full distribution, not just a single summary statistic, which matters because urban surfaces are spatially heterogeneous. A parking lot and a rooftop can behave quite differently, even within the same bounding box area. So let's go ahead and run section 6 of this script. This provides a summary statistic table stored in the variable df summary, where now we can quantitatively look at the mean land surface temperature in degrees Celsius, along with the standard deviation and the number of 70-meter pixels included in each of these areas. So we can see from this numerically that the nature preserve on night 1 was cooler on average than it was on night 2, which is expected. The standard deviation remains pretty close on both nights, although slightly lower on night 2, which is interesting. And then similarly in the commercial area, we see an increase in temperature from 23.7 degrees Celsius to 26.6 degrees Celsius on night 2 in the commercial area. But now let's look at this from a full pixel level distribution for each AOI. So that brings us into section 7 here of the script, which will show a violin plot with jittered raw pixels of the data values underneath. Let's go ahead and run this. So the points you see are the individual 70-meter pixels, and the violin shows the overall shape of the distribution, where the box shows the interquartile range, and the raw points show you exactly where the data actually are. A few things to notice here. First, the preserve distribution is consistently cooler than the commercial area on both nights, which we saw in the summary table as well. That gap is real and visible. Another thing to consider is the key comparison we're thinking about. Does the gap between the two AOIs change, or areas of interest change, from night 1 to night 2? Hold that question while we look at the next figure here. So in section 8 of the code, our core question is, after a full day of extreme heat on September 4th, do we still see the same thermal gap between the preserve and the commercial area on night 2? So we'll calculate the mean LST per area of interest per night and plot the absolute temperature for each area of interest across both nights, which shows whether each land cover temperature warmed from night 1 to night 2, and then also the thermal gap, which is simply the subtraction of the temperature of the commercial area minus the temperature of the preserve on each night. If this gap shrinks, the cooling benefit of the preserve is being reduced by accumulated heat stress. But if it persists or grows, the preserve is maintaining its function even under sustained extreme conditions. So again, we're using the ggplot library to make these plots, and I'm just going to go ahead and run section 8. Let's increase the size here for easier viewing. Panel A shows the mean LST trajectory for each land cover type across the 2 nights, with error bars showing 1 standard deviation. Panel B converts that into a single number, the thermal gap, defined as the commercial area mean minus the preserve mean. So in this case, we see the gap remains very similar on night 2, with slight 0.2 degrees Celsius decrease from 4.5 degrees C to 4.3 degrees C. This suggests that the preserves evapotranspiration and long wave emission are not overwhelmed by the heat event, at least not after 2 nights from the start of the heat wave. This supports the argument for urban green space as heat resilience infrastructure, not just as an amenity. Another possible outcome for subsequent analysis might be to evaluate whether the gap substantially narrows on further nights into a heat wave. And for this particular heat wave, there weren't ECOSTRESS data available around similar times after these 2 days for comparison, but that's something to flag and to consider if you're interested in studying another heat wave in a different location. So it'll depend on what data are available, but it's something that could be interesting to follow up with, looking at longer term multi-day heat waves and whether even certain natural areas might have a threshold beyond which sustained heat stress suppresses their cooling function. So this would be interesting to test in future work in other places, like I said. If a more prolonged period of the heat wave, the temperature difference between the 2 areas might actually decrease. So this is really one big urban heat island resilience question. And it's why nighttime ecostress data can be valuable for urban planning, not just because it captures the heat island effect, but because it lets us evaluate whether specific green infrastructure actually delivers measurable cooling when it's needed the most. These are the kinds of analyses that urban heat emergency planners, parks departments, and climate adaptation offices could use for their local and regional needs. Data like this can identify cooling refuges, evaluate where tree canopy investments will have the greatest thermal return, and map residential neighborhoods where nighttime heat exposure is most dangerous, particularly for people without air conditioning. Now I will turn it over back to Glenn.
All right, so moving on to section 4 now, which is land surface temperature downscaling. This brings us to the central idea of today's talk, thermal sharpening, or it's also sometimes called downscaling. It's often used interchangeably. The basic concept here is to take coarse resolution thermal data. Well, coarse here meaning 70 meters is actually, that is the highest resolution available from space, but still pretty coarse if you look at the urban environment, and then combine that with high resolution data that is well correlated with temperature, and that's the key here. And by doing that, we can recover the thermal detail at a much finer spatial scale. In this case, we're going to go all the way down to a 10-meter resolution. So this is a nice example that illustrates that, where we can go from what looks like blobs of cooler and warm temperature features in the environment here. This is over LA, by the way. down to 10 meters, where we can now start seeing very fine scale detail in the temperatures. We can see the differences between these hiking trails in Griffith Park, golf courses, freeways, building roofs, and so forth. So this opens up just a huge capability for us over specifically urban areas, but also in other natural vegetation areas as well. So as you can see, these are two more comparisons over different parts of LA. The one I just showed, Griffith Park on the top, and the bottom is over the Long Beach Harbor area. But as I said before, we can start really discriminating different urban features from one another. We can see, for example, the hot Costco roof versus the cooler cemetery. We can see the difference between the freeway and the much cooler fairways on the golf course, for example. So this animation, let's see if it works. Yep. This shows you the kind of detail that we're revealing from the 70 meter down to the 10 meter level. This is over Pasadena, and you can see the Rose Bowl highlighted here in the top left corner there. And after sharpening, you can see that we can resolve the distinctive sort of cool areas north of the Rose Bowl and the golf course, and also the hotter parking lots and roads to the southern part of the Rose Bowl. And we'll be going over that in quite a bit more detail in the tutorial, because this is actually going to be one of the venues for the upcoming Olympic Games in LA. And so this kind of high resolution thermal information is critical for heat intervention planning, and also planning for shade interventions in areas like this. This is, I think, just a fantastic image. This was also created by a summer student of ours last year, by Ashley Agatep. And it shows a downscaled image over Paris during an extreme heat wave in June 2022, where they actually had to close down a lot of the public spaces and museums within the city because it was so hot. This was sharpened and then overlaid on Google Earth, which is why you can see the structural features of the actual urban area come into play here. And I'll go through this a little bit, and I'll show you how to do this in the tutorial as well. And also it has its caveats too, which I will go through. But you can see individual neighborhoods, parks. You can clearly see the Seine River and other infrastructure standing out with the temperature. And it's this kind of intra-urban thermal detail that you simply cannot resolve at the 70 meter or higher pixel scale. As I mentioned before, in looking ahead, the Olympic Games is coming up in 2028 in LA. This is a sharpened ECOSTRESS temperature map, similar to what we did over the Phoenix area, where we pull out the temperatures at the street level. What I've highlighted here is the actual venues of the Olympic Games. And there's just tremendous potential here for designing, for example, heat mitigation approaches, planning where to add shade, both natural and man-made shade structures, and also cooling at outdoor events and watch party locations during the Olympic Games, and even extending these techniques to the coastal zone, coastal water temperature and water quality monitoring. So I will be going over some of these areas that we'll be focusing on also for the Olympic Games in the tutorial. So moving on to some theory of the actual downscaling. Statistical downscaling, what we call sharpening, is so what we're doing is we're disaggregating a coarse scale thermal pixel into its subpixel components. And the trick here is to use auxiliary data that has a higher spatial resolution that is statistically correlated with the land surface temperature, which is our target here. And so this illustration shows that quite nicely. It's from Chen et al. And colleagues, and shows how a single coarse pixel, A1 in this case, gets disaggregated into 4 subpixels, B1 through B4, using the relationships learned from the higher resolution covariates. And we'll actually be doing this at a finer scale. So we'll be taking one ECOSTRESS pixel and dividing it up into 50 different individual pixels. So that's 70 meter to 10 meter resolution. So at the highest level, the workflow looks like this. We start out with ECOSTRESS at 70 meters as our target variable, and then we assign predictive variables consisting of Sentinel-2. This is a European Space Agency sensor that was launched in 2015 and generates 10 and 20 meter high resolution visible shortwave infrared data. So that is our primary predictor here, is the surface reflectance from Sentinel-2. We also include land cover types, built-up fraction, and also the elevation. The output then is we run that through a random forest regression. We train the data at 70 meters, and then we predict the final sharpened LST at the 10-meter scale. So you may ask, well, why do we use Sentinel-2, the spectral reflectance bands? Firstly, we could use there are some 20-meter bands as well that we have been using in the past, but in this tutorial, we'll be focusing on the 10-meter bands, which gets us down to that sort of street level resolution that we're after. So the bands are located in the visible part of the spectrum, so between 400 and 700 nanometers. This is the part of the spectrum we actually see with our naked eyes. We have 3 bands there, bands 2, 3, and 4, blue, green, and red. And so these bands, the surface reflectance of these bands correlate with temperature, because the more reflective a surface, the less the surface will be heating, and therefore the cooler the surface will be. And this is a bit of a generalization that doesn't always occur, but it's a good statistical correlation with the temperature. We also then have band 8, which is the near infrared band. This is right on the edge of the infrared spectrum that ends at around 900 nanometers. And this band has actually the opposite information to the other 3. So it's sensitive to vegetation health, chlorophyll content, water content, and it's one of the strongest predictors, in fact, of LST spatial variability in urban-rural gradients whenever you have vegetation involved. And we'll go over that a bit later as well. So why does this work? So what I've plotted here is land surface temperature. Each pixel here has an actual temperature on the ground. And I've plotted it versus the NDVI, which is the normalized difference vegetation index. Some of you may have heard of this. It's a band ratio between band 8 and 4 that I just showed you. And generally, high NDVI values are greener vegetation and are generally cooler, and the opposite is true with low NDVI values. So because surface temperature is statistically tied to these surface reflectance properties, the bare low reflectance surfaces like roads, for example, run hot, vegetated high NDVI surfaces stay cooler. And then on the bottom end of the spectrum here, we have high albedo surfaces like white roofs, for example, or white roads are also cool. And so there's a sort of triangular nonlinear relationship between surface reflectance and land surface temperature. And these are the exact nonlinear relationships that our machine learning model is going to be learning at the 70-meter scale and then applying down to the 70-meter scale. So why sharpen ECOSTRESS down to these levels? Like, what are the primary urban applications and what are our reasons for doing this? Well, there are 6 concrete reasons here. Firstly, we're able to, of course, resolve urban features from the 70-meter down to the 10-meter scale, streets, parks, rooftops, blurred together at the 70-meter scale, and we're able to resolve those. It lets us validate heat interventions at the scale at which they're actually deployed. So think of cool pavements being applied over cities, cool roofs. It also dramatically reduces our mixed pixel error, especially when we're in sort of heterogeneous neighborhoods. It aligns with the parcel level planning data that the city agencies actually already use. It sharpens heat vulnerability mapping in underserved poorer communities, which is critical, for example, downtown LA. And the last part here is really critical, is that we apply this residual correction, which we'll go over in detail, which means we actually preserve the radiometric accuracy by normalizing to that of the ECOSTRESS instrument. So we're adding spatial detail, not inventing temperatures, if you will. And I'll show you some of these examples in the next few slides. So at 70 meters, you can think of, we have a small city block scale temperature. And then after the sharpening, we end up with 10 meters, which is equivalent to 49 pixels. And so we have a 50 times improvement in the spatial resolution using this methodology. So why random forest for this task? Well, it's inherently available within Google Earth Engine, which is great. And the basis for which it works is you take an ensemble of these, what we call decision trees. Here I've outlined them, tree 1 through n. Typically, we start out with about 100 trees, but you can increase or decrease that value. And each of these is trained on a random subset of features. So what I mean here by features is that it's a subset of different combinations of the predictive variables and also the different pixels within the scene. And so we then end up with a final prediction, which is an average across all of those trees. So, and it's a very powerful technique because it, as I said before, it handles these nonlinear LST and surface relationships. It's robust to outliers because it's able to generate an ensemble mean, which reduces the variance in the data. And it's also transferable across scale. So we train at 70 meters and then we can predict at 10 meters. Also, something that comes out of the random forest, which is really interesting, is a feature importance information, which identifies which of our predictors were the most sensitive or the most important in arriving at our final result. And I'll go over that in a minute as well. So from sort of the high level, this is what the sharpening in Google Earth Engine is going to involve. These are the different steps. We start with our training data and our target variable of ECOSTRESS LST at 70 meter. We then train the random forest model within Google Earth Engine at the 70 meter scale, and then we predict the 10 meter final temperature, and then apply this residual correction, which means we upscale the 10 meter prediction to 70 meters, subtract from the original 70 meter observation from ECOSTRESS, and then we add that residual back to the 10 meter result. And I'll show you that on the next slide. So these are just some cutouts that are made from within Google Earth Engine at various steps along the way throughout the sharpening process. This is a cutout over an area, a heterogeneous urban area here in LA. So on the top, in the middle here, you can see the original ECOSTRESS LST at 70 meters. The next step is the initial downscaled LST. So this is after applying the model at 10 meters, we end up with this result. So you can see immediately fine spatial detail coming out within the urban environment that correlates nicely with the actual visible image on the top left. Now, you can also see that the actual absolute values of the temperature here are quite different to the actual observed data in the top. We don't see these sort of hotspots in the lower left and bottom areas. So then after the residual correction I just explained, we upscale the 10 meter to 70, subtracted from the 70 meter ECOSTRESS, and we end up with this residual corrected final LST at 10 meters, which preserves the actual radiometric information in the original 70 meter resolution image. And you can see that these correlate a lot better now. So I'll quickly go through what these predictors look like sort of at a much larger scale over the entire LA city and county area. This is the area that we'll be focusing on in the tutorial today, by the way. So this is the Sentinel-2 surface reflectance. This is for band 8. This is the near-infrared band at 10 meter resolution. This is provided by Copernicus and European Space Agency through Google Earth Engine. And so we'll be using the blue, green, red, and near-infrared bands. This is the near-infrared band. And you can see here immediately areas, sort of features that pop out. For example, these wide areas that you see here with high reflectance are in fact green spaces. So these are pretty much the golf courses around the LA region, which have a high band 8 reflectance because they're chlorophyll active green types of irrigated vegetation. And conversely, we have very low reflectance over dense urban paved surfaces, mostly human-made types of surfaces. This is the NDVI, as I spoke about. It's a band ratio between band 8 and band 4. High NDVI values correlate also to dense and green vegetation, and conversely, bare soils and senesced vegetation or urban materials have a very low NDVI. And conversely, with temperature, of course, high NDVI values should have cool temperatures and low NDVI values should have hotter temperatures. The other predictor here that I'll show is the built surface fraction. This is from the European Commission's Global Human Settlement Layer available within Google Earth Engine. And this data captures gradients in urbanization that other land cover, land use categories alone aren't able to capture, and especially useful in mixed peri-urban regions where you can see the fraction of the built-up area changing very rapidly into more vegetated rural regions. And then our fourth predictor here is actual elevation. This is from NASA SRTM's 30-meter product. We then resample that to 10 meters for the training. And elevation really matters, in fact, in this region because the lapse rate alone explains a couple of degrees of LST variation, especially across these hilly areas of LA. Think of the Santa Monica Mountains here, the St. Gabriel's. And we want the model to learn that effect explicitly rather than sort of baking it into the residuals. And then lastly here, the star of the show, this is the ECOSTRESS land surface temperature at 70-meter resolution. This is the actual image we'll be working with in the tutorial next. This was, I believe, on the 14th of August, 2020. This is an extreme heat wave event in LA. You can see the extremely hot temperatures here in the San Fernando Valley in the northern part here that is insulated from the cooler ocean breeze. You can see strong gradients here along the coastline, having much cooler temperatures, and then increasing to much hotter temperatures in the interior urban areas. This was acquired at 4 p.m. in the afternoon, so one of the hottest parts of the day. Also, you notice that there's no cloud artifacts in this image. So there's a very nice clear sky day, which is why I chose this image. Also notice that very distinctive cool islands here. You can notice these sort of cool little areas within the urban environment. And again, these are mostly golf courses, parks, green spaces that are 20, 30 degrees cooler, in fact, than the surrounding urban landscape. And then I mentioned the feature importance outcome of the random forest. And this is really interesting and something that I will show you how to derive from the data in Google Earth Engine as well. And it's how the predictors actually rank in the trained model in terms of feature importance. So in this case, elevation actually came in at the top at 17.6%, followed by the 4 sentinel bands, all clustered around 17%. So these 5 predictors are driving most of the information that is provided in the random forest, getting us to that 10-meter scale. The build surface actually contributed about 11.4%, so pretty significant, but the actual land use, land cover map, which I included in this example, had a very low information content. And that's actually because it's derived from the Sentinel-2 reflectance data. So essentially, you don't want to add in variables that are correlated with each other. So we should probably remove the land use, land cover from this case. All right, so that's it on the theory. We'll now get on to the fun part here, which will be the actual hands-on exercise, where we'll be diving into Google Earth Engine and actually showing you how to produce these really nice, striking maps of the urban environment. Before I get started here, I just want to preface this by saying that we do have everything I'm going to go through here, literally every step and click I'm going to make is actually available on a tutorial that we created in Microsoft Word. So we'll make these available so that you don't have to, look through the video tutorial again and listen to me going through it all. You can actually follow along step by step, every click and every move I make on this document tutorial that you can reference for later use. So starting out from the beginning, we're going to open a web browser. For example, it tells you here, go to code.earthengine.google.com. You'll also need to sign up for a free Google account, and you can do that by going to this website, earthengine.google.com, sign up. We also have a link to a YouTube video in our resource page, which actually shows you step by step on how to actually sign up for a free account on Google Earth to start and be able to do this tutorial. So this is what you'll end up with if you start your Google Earth Engine page. On the left are your various scripts or pieces of code that you can store. We then have a docs page. You don't need to look at that. The assets are actually data that your code can operate on. We won't go into that either. So what you'll be doing is you'll be clicking new here. It's a big red icon. Okay, click new. You'll go to file, give it a name. I'm just going to call it sharp, but you can call it any name you want. And it'll create a new file, which you then can paste directly the code that we're going to provide for you, which is the EcoSharp v1.1 code, which you're seeing right here. And so that's how to get started. So you'll click Save, and then you have your JavaScript Google Earth Engine code ready to go. So a couple of just orientation things here. First, in the center, of course, you can see the actual code. This is JavaScript code. You don't need to even look at this if you don't want to. But you'll see the buttons on the top here showing how to run the code, reset the code. On the far right panel, you can see something called a console. And this outputs various types of information that the code runs, and we'll see that in a minute. For example, some stats on accuracy, what data was used at what time. Tasks we'll also go over when we're going to finally export this data to a GeoTIFF file and open it in QGIS. You'll be able to run a task here to export it directly to your Google Drive account, and we'll go over that in a minute. Okay, so getting started, we are going to start over the Los Angeles region. Of course, I said we're going to start with that image that I just showed you. If you grab this little toggle here, you can actually move the map up and down to make it easier for you to actually see the data coming in. So I'm going to move it right up for now, and we're going to hit run, just simply hit run. And what you end up with is a user interface panel on the left and a user interface panel on the right. What you'll see on the left, let's start with the left, you'll see a date range here. So in this case, I've put in a single date, the 14th of August, 2020, where I knew we had this scene over Los Angeles during the heatwave event. If you were to change this and say, for example, go from June till July 2020, what the code will do is it'll take all the ECOSTRESS observations over that time and generate a mean composite image over a date range. So we can either look at a single date for a single image or create a composite from a date range. You can also see additional summer years. If we clicked on those additional years, we can create a composite over consecutive years over a fixed date range. So if we want all the summertime average temperature across the entire mission period, we can click on all of these years and generate a mean composite average. And so this is often useful for city planners and managers. They want to know what is the baseline average summertime temperature that we've experienced over the last 5 years. The next part here is the local time window. So this is in hours of day. What I've done is here is I've converted this. You can convert to different time zones around the world, and that makes it easier where you don't have to deal with UTC time. So we're in Los Angeles. We're going to click Los Angeles time zone, and in this case, we're going to look at all hours of the day. We know there's one scene here. You can change this to, if you just want the afternoon hours, say 12 till 18, we'll get all the data from the hottest times of day, 12 till 6 p.m. But let's go back to 0 to 23. The next part here is the max cloud tolerance. So if you want less cloud on the scene, you can decrease this value. You can go down to 10. I would suggest for a long-term composite that you go down to 10%. So we don't want more than 10% of cloud on the scene. The cloud is already screened, by the way, so it won't be included in the data, but we don't want to combine images where part of the image is missing and then we combine it with other images and you get some artifacts coming through. So I would use 10 for a composite and use 30 for a single image is fine. Then you have an option to draw a custom rectangle. So if I click on that and click activate selection, and we just want to do the San Fernando Valley, for example, we can drag and drop and run our sharpening over that specific area. So I'm going to clear that because what we're actually going to do here is go to an ECOSTRESS tile, and we're going to run the code on an entire ECOSTRESS tile over this region. So if I activate that selection, and I click on anywhere in the center of the LA map, it's going to give us the tile boundary for this specific area. And I won't go through the details of the tile boundaries, but the Sentinel, we use the Sentinel-2 tiling structure here, which is based on the NGRS system. This is the military grid reference system, where the Earth is divided up into these fixed tiles. They're roughly about 100 by 100 kilometers wide. And you can go and Google this and learn more info on that if you want. But this is the tile we're working with. It covers the whole LA area quite nicely, as you can see. And on the bottom left here, you can hit run and export. But before we do that, let's go over to the right here where we can see we have some other options here which are really useful. So we can choose exactly which sharpening predictors we want to use. The Sentinel-2 bands here are required, so that's always going to be clicked. But we can click off the land use. As I said, it doesn't have a huge influence on the final result. We probably want to include the surface fraction and elevation. Those had significant feature importance values. I'm not going to include the NDVI just because that information is already baked into our reflectance bands. But you can, for example, use NDVI and the reflectance bands, and you can see what kind of data that provides, for example, over ag areas that may be more beneficial. Next, we can choose the temperature unit here. So we can go from Kelvin, which is the standard unit, the scientific unit that ECOSTRESS comes in. We can switch to Celsius and then Fahrenheit. Here, I'm going to stick with Fahrenheit. And then we have the export options. So this is, the actual data that we want to look at in QGIS eventually is going to be the LST, 70 meter, 10 meter. Don't worry about this model ARSET. As I mentioned before, in the top left, if you did export the ARSET, you'd have this available in your assets here, and then you could apply that random forest model to another scene if you wanted later. You don't have to do the training on every scene, but that maybe should be left to another tutorial. Then you can export also the predictor layers if you want to look at, for example, the images I just showed you in the slides with the Sentinel bands, NDVI, land cover. You can export all of those if you wish to. So I'm going to leave those alone. And if we click run and export, you can see the bottom left here that it's already found all the data. It's already on step 2. It's now sharpening the data to 10 meter resolution. And you can just see how quickly this operates. We already have the LST pulled in. This is the ECOSTRESS land surface temperature I actually just showed you in the slides. And while it's running through its sharpening training process here, if you click on the layers here on the top right of the image, you can actually toggle between the different predictors in the LST that have been brought in by Google Earth Engine. And also on the right here is an opacity slider, which is kind of cool. You can see how the image fades in and out of the background Google Earth map. So, while this is running, I guess you can play around with the LSTs and the other data here and look at what the data looks like. And then, okay, let's go through the console here. There's actually a lot of information that gets printed out in the console on the right-hand side here. It just gives a summary of the actual options you use, the date range, the time, cloud tolerance. It'll show you the actual MGRS tile number that ECOSTRESS relates to here. This is 11 SLT tile. And then it will show you the actual Sentinel-2 scene that was used. So the code currently looks at Sentinel-2 data within a month of the ECOSTRESS observation. So in this case, you can see we found a scene on the 12th of July. ECOSTRESS scene was 14th of August, so not exactly a month, but close enough. The summertime period, vegetation is not going to change too much, for example, over LA, so it's fine that it's within a month. The code automatically looks for very clear Sentinel-2 scenes. So in this case, there's barely no cloud on the Sentinel-2 scene. That's pretty important. You should probably check that, but the code will automatically check for cloud-free data. There's some other information here. It shows the data that you want to export, and then also it actually shows the sharpening accuracy, which is the initial 10 meter resolution image that I showed earlier. Now, after normalization, this actually dramatically reduces in the bias and the RMSE after we do the radiometric normalization to ECOSTRESS. So these numbers may look pretty big, like 8 degrees Fahrenheit, but they end up being pretty small in the end. And I actually might change this so that produces the stats after we've done the radiometric normalization. Anyway, let's go into tasks. This is the important part now. We see our 3 tasks here are the 3 data sets that we chose to be exported to our Google Drive. So I've already done this, so we're not going to wait and run this in real time. It actually takes quite a bit of time because if you click on the 10 meter here and hit run, it'll give you the task name. You can change that if you want. Shows the coordinate system, the resolution, and the drive shows the drive folder that it'll create for you if you haven't created one in your Google Drive account. And then the file name and the file format, of course, here is a GeoTIFF. So it has the spatial information included within the data. And so if you then hit run, you'll see that there's a submitted task. It will be running and it'll show the time it's taken to run. You do that with the others, and then you end up with your data in your Google Drive. So in my case, this is the GEE ECOSTRESS folder. And you can see a list of GeoTIFF files here. You can see I have quite a few because I've obviously been doing a lot of testing on this over the last few months. And then you can click on the right side. You can see these three little dots on each file. Click that, hit download, and it will download your file to your desktop. Okay, so let's move on to the next part here, which is actually visualizing this data in QGIS. So just to recap, everything I've just been through is on this Google Earth Engine running EK-Sharp version 1.1 tutorial. So you can go through that step by step at your own pace if you want. And then we're going to be available for questions as well. So similarly, we have a full tutorial on the visualization in QGIS. So every click and step you see coming up now is laboriously documented in this file. So you can go through this at your own pace as well. There's little tip boxes. There's all kinds of nice little snippets of information here. And it ends with even a quick reference and troubleshooting guide. So really nice reference to have handy while we go through the actual tutorial. So let's open up QGIS. I already have mine open. There's a link in the resources on how to download QGIS, and I'm pretty sure most of you will have it already from Savannah's tutorials. So let's begin. So if you go to the top left, hit project and hit new, we start a new project. Go into project, save as, and call it something. So let's call it ECOSTRESS sharpening. And I'm just going to save it in my documents folder. So we have it saved. We have our project saved. We're not going to lose all the data that we're doing. So next step is we want the Google base map. This is really important and very useful to have. So go up to right at the top where it says HCMGIS, click on that, go to base map and click on Google satellite. So now we have our Google nice satellite base map. Next, we go to layer, add raster layer. And on the source here, you can see I already have mine that I've uploaded, but if I click on the right here with the three dots, it's going to take us to a folder where mine was in ARSET, and I'm going to upload firstly the 10-meter LST, hit add, close, and I'm going to do the same thing for the 20-meter, the 70-meter layer. So if we go here and it's 70 meters, add. Okay, now we have on the bottom left on our layers, you can see we have the 70-meter product, the 10-meter product, the Google satellite map. Now, we're not seeing anything yet because we actually have to zoom to the layer. So if we right-click and hit zoom to layer, we'll now see the map centered on our image over Los Angeles. And it's all default in grayscale. That's kind of boring. We don't want that. So what we're going to do is we're going to double-click or right-click and hit properties on our file. We end up with this page. We start with symbology. Go to the top where it says render type, hit single band pseudo color. We don't want it in grayscale. Then for the min-max value settings, I'm going to click this arrow. And what I typically like to use is I don't like to hard code the min and max because it's going to change for every scene. So I typically like to use between 2 to 5 of the lower percentile of data. And then on the high side, I either go from 98 to 100. And it kind of varies on the area that I'm looking at. So let's use those values for the color ramp. I actually, this is really a personal preference. You can go magma. Spectral works pretty well. If you look at all color ramps here, you can see there's a really wide variety of color ramps. I'll show you a little trick. The one that I actually like is if you go to create color ramp, go to catalog CPT city. I know this is a bit much, but QGIS, and then all by author on the top right. I really like this temperature map, so let's use temperature. All right. So if we click and we hit apply, now we can see our image nicely scaled in color scale, where the blues are the cooler colors, reds are hotter colors, so it's pretty intuitive. And we're just going to go ahead and do the same thing quickly with our second band. I'll go through this pretty quick. Done it already. Change our percentile thresholds to 5 and 100. And we'll go with our temperature color ramp, which again I have to add. I actually need to save this one so I don't have to do this every time. I haven't. Temperature, okay, apply. Okay, now we have both data sets together at the same color range and more importantly in the same color ramp. So firstly, what we can do here, let's go into this area in the San Fernando Valley. Let's look at this little blue island here and see what's going on. So we zoom in here, we can toggle these on and off, which is really really useful. So you can look at the Google background image. Yep, it's a golf course. So this is two golf courses in the San Fernando Valley. And on the right side is an actual park. This is an actual area where people fly remote control aircraft, in fact. This image here, this must have been in the spring because everything looks pretty green. And in actual fact, during the summer, this is pretty barren and bare soil, very hot. And you can actually see that in the ECOSTRESS data. You can see the very hot temperatures here over the park and then much cooler over the irrigated golf course. So looking at the 10 meters, so we just see two big blobs, right, at 70 meters. There's not much detail there. If we go to the 10-meter scale, now we can really see the detail pop out. So we can start seeing the actual trees along the fairways of the golf course that are cooler than the fairways. It's pretty cool. You can see this vegetated waterway going down the center of the golf course. You can see roads. You can see specific freeways that are hot. So it just opens up all this detail to what's actually going on in the urban environment. On the right here, you can see building roofs and parking lots that are distinctive and have distinctive temperatures from each other. And if you zoom into this sort of suburban area, you can actually see the temperature of individual trees. So this is really cool. You can actually see the cooling impact of trees and green grass yards in this environment. You can see down to the level of whose roof is the hottest, right? So you can see the dark roof right here. You can see my cursor. This sort of bright red spot is actually someone's very dark black shingle roof. And this cooler area right here, you can see it's actually a lighter shingle color, which is a lighter temperature. So really cool in that you can really zoom in to very fine scale detail on temperatures. Let's go to another area quickly that I really like. I actually used to live close to this area and actually play on this golf course quite a lot. This is the Griffith Park golf course. On the edge of Griffith Park. And it's really nice because there's sharp gradients in temperature here from the golf course to the freeway into this more industrial complex zone just off the western edge of Glendale. So at 70 meters, again, not much detail. You can see the broad outlines of where the hotspots are, but it's really only when we go to the 10-meter scale that you start seeing the actual temperature of a hiking trail. So these are bare gravel trails that are hotter than the surrounding landscape. Again, trees lining the fairways. And what's pretty interesting here is, let me change the scale a little bit here. This is where, as I mentioned, you want to change the min and max of the data depending on where you want to look at to increase the contrast. So this looks a lot better for this area. One thing I wanted to point out here, note that this is the 134 freeway running here along the northern part of the image right now. You can see how much hotter that freeway is. It's running east-west. So it's directly being illuminated by the afternoon sun. There's no intervening trees or shade on the freeway. Whereas if you look at the 5 freeway south, right next to the golf course here, look how much cooler it is. It's actually 10, 15 degrees cooler. And if we actually zoom into Google Earth here, you can see that there's actually a very tall trees lined up on the corner, on this side, on the western side of the freeway, which provides a lot of shading. And of course, you have Griffith Park here, which provides also even more shading during the afternoon hours. You have a much cooler freeway. So it just shows the level of detail that we can get to at this resolution by looking at the actual differences in freeway temperatures, which I think is really cool. Okay, then the last quick thing I want to show you here before we actually get to exporting the data as actual imagery. Let's go to the Rose Bowl. This is actually one of the venues for the World Cup and the Olympics coming up. So this is a pretty important area that they're going to be looking at to try and implement heat mitigation efforts. If we look at the Rose Bowl here, we have these huge, massive parking lots, right? These are naturally going to be very hot surfaces. And this large field actually gets very hot during the summer too. It's mostly dry synest grass. So looking at the 70-meter data again, we can see there's some hotspots around. We can't clearly see exactly what they are, but it's only when we go to the 10-meter scale that you can see, yep, these are these large parking lots and roads surrounding the southern part of the stadium, which are 20, 30 degrees warmer than the golf course, for example, to the north. And this, if you can imagine, if there's airflow and wind coming in from the southwest and southern parts of this image, that you're going to get a lot of heat advection from these hot surfaces into the stadium. And so these are the kind of areas that we want to target for heat intervention during upcoming events, but also just for the future sustainability of heat in the LA region. Okay, so what if we wanted to export these images? Before I do that, I wanted to show you another cool trick that sometimes we use, but not very often, because physically it doesn't stops making much sense. But if we go into symbology again, go all the way down to layer rendering, blending mode is currently normal. If we hit overlay, what it's going to do is actually overlay the data directly on Google Earth Engine background map. So it's pretty cool. You can see almost the 3D structure coming through with the temperature overlaid on top. And this is how we generated that Paris map that I showed you earlier. But the one caveat here is that you can see the building roofs here, which are white, actually come through as looking white, whereas they lose their actual temperature color here, which should be the dark red color. The same with green spaces, they come out looking green because blue on green gives us kind of a green. So if you can deal with that, that's fine, but it just provides a really nice, pretty image. Okay, let's go back to the normal. And then the last thing we're gonna do today is we're gonna show you how to actually export a PNG image or an image in any format that you like. So let's put the image at this scale. You can change the magnifier on the bottom right, by the way, to any scale you want. And you can just use your mouse to zoom in and out. I'm gonna leave it at this scale. Go up to project. We're gonna go to new print layout or Control P. Let's call it LA Sharpen. You can name the print layout anything you want, really. You end up with this sort of blank palette here. What you're going to do is hit Add Item at the top, Add Map. Okay, now you're going to get across, and what you want to do is click and drag across to fill this entire blank canvas space. And what it's going to do, it's going to render the map that you see in QGIS in this region. So now we can do a couple of things. We can go to Add Item, add a scale bar, for example. There's a scale bar on the bottom left. Let's add a north arrow, is also kind of typical. Shows the north up direction. You can also add, what's pretty important actually is a legend, which shows us the the legend of the color scale. I really don't like the legends that QGIS comes with, to be honest. So usually I actually do this kind of work in R or MATLAB or Python, but this is possible. So now you see twos because we have two layers in our QGIS. So we click on that, go to the bottom right here where it says legend items, click auto update. Let's move this up. And let's click on the first one here because this is the 10-meter map and hit this minus red button. So we delete that one. You can also delete the actual names, I believe, if you like. But anyway, that's what you can produce with your map as well. And then if we go to layout, export as image, you can then export your image in typically PNG is a pretty good format to do it and preserves the resolution of the image. You can also output in TIFF or JPEG and then click save. And then export resolution, you want to go at least 300 dpi for looking at, for importing these into PowerPoints or anything else. Hit save and you'll have your image saved. Now, the other way we can do this without adding all this other fancy stuff to the image is if we just want to directly export this image right here, go to project, import, export map to image, change the DPI, 300 DPI, hit save. And again, I'll just name it something, and you can directly save just this image right here. Sometimes what I do is, in fact, is I crop out the color scale on the left here, and I save that and include it with the image, which makes it a little easier if you want to do something in QGIS. I think we have a little bit of time left. The last thing I wanted to go through here was how to actually do some quantitative analysis within QGIS. So this will take another minute or two, and this is all laid out in the tutorial again. So say I want to see what is the temperature difference between this golf course and this sort of Bear Park area. So what I'm going to do is, it's a little bit elaborate, but if I go to layer, let's see, vector, and layer, add layer. Actually, I've already forgotten how to do this myself. So let's actually, this is a good idea. Let's go to the QGIS tutorial and let's figure out how to do this. So create zone polygons. Okay, zonal statistics. Here we go. So layer, create layer, new shapefile layer. Okay. Layer, create layer, new shapefile layer. Let's call it zones. Geometry type, we want to do polygon. And then we're going to click OK. Go to zones again, right click on zones, hit toggle editing. It's this with a little pencil mark. And then click this sort of green icon, which is adding a polygon feature. Looks like a little putting green. And then you can start drawing your polygon to any shape that you wish. So let's draw the entire golf course here. We then right click, go to ID, let's call it 1. Here we have our first one. Let's click on the second one, which is this little really hot zone park. Right click, call it a different ID, number 2. Okay, then we have our 2 different zones. Now what we can do is go into processing, toolbox, search for zonal statistics, double click zonal statistics. We have our input layer as the zones that we just created. Raster layer, we want the 10-meter data. And we want to see, let's do the standard deviation, the mean, that will be important, and the min-max. Okay, so run, close that. And if we go to zonal statistics and open attribute table, okay, there we go. We finally have the actual quantitative results here. So the ID1, which is the golf course, mean temperature of about 100 degrees Fahrenheit. The park next to it was, 20 degrees hotter on average, 120 degrees, but up to 128 degrees Fahrenheit. So that's really hot. And the minimum golf course temperature here is about 87. So you can see some zonal stats. I usually do this kind of thing in R and MATLAB and Python, but I just wanted to show you that you can actually do this in directly in QGIS if you really wanted to. So I'm going to remove that layer and remove that layer. And then see if I can remove this. All right, and then if the last thing here is to double click on your file again. If you go to transparency, you can change the transparency, let's say 70%. This is a really cool trick to do as well. Now you can start seeing some of the background Google Earth imagery coming in the background. And it just gives it a nicer look. So that's it. That's all I'm going to show you today on this tutorial. Again, you can go through the actual documents, which we'll be sharing, that will give you the full step-by-step on how to do what I just did in the QGIS tutorial and the sharpening tutorial. So thank you very much, everyone. I hope you enjoyed that. And we'll be here for questions when this is finally presented. Thank you.
Thank you, Glenn, for leading us through the Downscaling ECOSTRESS LST demo. I will now provide a recap of our training. Here's a summary covering all 7 learning objectives from our thermal remote sensing training. First, the physics of thermal emission. All matter above absolute zero emits electromagnetic radiation. Planck's law, Wien's displacement law, and the Stefan-Boltzmann law govern how much energy is emitted, at what wavelengths, and how sensitively it responds to temperature change. Earth surfaces, at around 300 Kelvin, peak near 9.7 micrometers, placing land surface temperature retrieval squarely in the 8 to 14 micrometer thermal infrared window, a range of purely emitted energy with no solar contamination. Real surfaces are not perfect black bodies. Emissivity being less than 1 encodes the composition of and the roughness as well as the mineralogy of these surfaces. And a 1.5% emissivity error propagates to about 1 Kelvin of LST error. The temperature emissivity separation algorithm, or the TESS algorithm, used by ECOSTRESS, ASTER, and MODIS 21, simultaneously retrieves both temperature and spectral emissivity, making it far more accurate than split window approaches over bare, arid, or geologically complex surfaces where split window can err by 3 to 10 Kelvin. Unlike optical sensors, such as Sentinel-2, Landsat in the visible and near infrared, which detect reflected sunlight and go dark at night, thermal sensors detect emitted surface radiation around the clock. This enables nighttime observations of heat retention, urban cooling failures, and ecosystem thermal stress, signals that are invisible to any reflectance-based product. From ASTER's 16-day revisit and 90 meter pixels to ECOSTRESS's diurnal sampling from the International Space Station, and looking ahead to the EAGLES, or formerly known as Surface Biology Geology mission, Trishna, and LSTM, each mission trades off spatial resolution, temporal frequency, and spectral coverage differently. Choosing the right one depends on whether your application demands long-term record, fine spatial detail, or multi-time of day sampling. Thermal data underpin not just urban heat island characterization, but many other applications, including evapotranspiration estimation, agricultural drought monitoring, ecosystem thermal stress detection, long-term climate trend analysis, such as lake warming, expanding hot nights, and surface energy balance modeling. making accurate thermal infrared retrievals consequential not just for remote sensing, but for climate projections, ecological conservation, and public health decision making. In the hands-on EcoStress data processing in R, we walked through a complete R-based workflow, accessing EcoStress LST and emissivity collection to geotiffs via peers, applying quality control bit masking and cloud masking, converting Kelvin to Celsius, defining areas of interest, and producing violin box plots and thermal gap figures, demonstrating how nighttime LST at the Chatsworth Nature Preserve remained measurably cooler than the adjacent commercial area, even after a full day of extreme heat during the September 2024 LA heatwave. For the component of the second demo, downscaling EcoStress to neighborhood scale with machine learning, we saw that because the physics of thermal emission limits spaceborne thermal infrared resolution, for instance, 70 meters for EcoStress versus 10 meters for Sentinel-2, Part 2 introduced a random forest downscaling workflow in Google Earth Engine that leverages high-resolution Sentinel-2 spectral indices, NDVI, NDBI, NDWI, as predictors of land surface temperature, exploiting the strong physical relationship between surface cover type and heat retention to sharpen EcoStress imagery to 10 meters and reveal block-level urban heat patterns invisible in the native product. Reminder that the homework for this training opens today on June 2nd. It is due 2 weeks later on June 16th, 2026. Upon attendance of both sessions, as well as completion of the homework by the due date, participants will receive a certificate of completion for this training. I would like to acknowledge my fellow colleagues in the ARSET Ecological Conservation Team who have supported the creation of this training: Sativa Cruz, Juan Torres Perez, and Justin Fain. I would also like to acknowledge the ARSET program staff who made this training possible, including Selwyn Hudson-Odoi, Maria Maravito, Suzanne Monthi, and Melanie Follett. We encourage you to check out our website, as well as the ARSET YouTube channel linked here in this slide. You can also join our quarterly newsletter to stay up to date on our latest trainings by sending an email with no subject to arset-join@lists.nasa.gov, and then follow the instructions sent in the response. The contact information for myself and our other guest instructor, Glenn Hulley, is also here if you'd like to email us directly with specific questions about this training. Here is a list of references for this training. These are all great places to start to dive deeper into the material that we have presented. Thank you all for your participation in this training. We will now transition into the Q&A. So let's address a few questions now, and then the remainder of the questions we'll address later this week. So I want to first just thank Dr. Glenn Hulley, who has joined us as for this training. Thank you so much, Glenn, for your time and expertise. And yeah, let's dive into the questions. Question 1 asks, given the possibility of a moderate to strong El Nino this year, how could El Nino interact with long-term climate warming to increase urban heat island risks and affect glacier mass balance? In particular, how might these impacts differ across regions, such as tropical cities, mid-latitude urban areas, mountain glaciers, and polar ice environments? Glenn, would you like to answer?
Sure. Yeah. I mean, starting off, it's it's a pretty broad question and interdisciplinary, covering a lot of different um, science areas and disciplines. But this is our best answer on the fly. Is that we are getting an El Nino likely this summer. It's going to be strong. NOAA is predicting that as a result, we're going to have one of the Earth's warmest years on record coming up, 2026, 2027. So in general, the El Nino has a positive impact on temperature anomalies. So we're going to expect warmer temperatures overlaying on an already warming climate, and that is going to ramp up the UHI effects that we typically experience in urban areas. I won't go into detail about how this affects different regions. I'm actually not a major expert on El Nino and other events like this, but I know, for example, in tropical cities, they should expect less cloud cover, so you can expect increased solar loading, increased temperatures, drought stress vegetation, and combined with higher humidity, it's probably going to be subtropical areas that are going to experience the most detrimental effects. Mid-latitude urban areas, think of western coast of California, for example, and LA, just from experience, usually results in drier conditions and warmer conditions, less rainfall, higher temperatures. So in general, the El Nino events will ramp up and increase the UHI effect.
Thank you. Question 2 asks, how does this urban cooling effect during the day differ depending on surrounding land type? For example, arid versus agricultural versus forested.
Yes, so this was actually nicely demonstrated in the earlier presentation of two areas, Delhi and Athens. Two quite different cities, but Delhi, you think of a typical Mediterranean environment, and what happens there during the summertime is that the surrounding rural areas, in Delhi, it's actually mostly agricultural regions, have a very dry, barren, senesced vegetation and an increased exposure to bare soil. And so typically we see a cool island effect during the daytime in cities like that. Especially in Delhi, we see a pronounced cool island effect. If you have a city in a tropical region, surrounded by dense forest, the reverse is going to be true. The forest is going to be dense vegetation, typically is going to be 10 to 20 degrees cooler than the urban surfaces, which heat up much faster than vegetation. So you'll see the classic urban heat island effect, which most people are familiar with.
Great. Let's do 2 more questions. So the question 3, why does near surface ozone concentration increase in the summer?
Yeah, that's a good question that most people don't realize, what physically what is happening there. And it's actually a photochemical reaction, meaning that it's actual VOC, so volatile organic compounds from car exhaust, just think pollution in general in the city, that reacts with sunlight to produce ozone. And so the hotter it is, the sunnier it is, the more ozone is going to get built up, especially near the surface, whenever you have high pollutants in the urban environment.
Thank you. Question 4, which will be our final question for today, asks, can ECOSTRESS land surface temperature data be integrated with hydrological or watershed models to jointly analyze urban heat, evapotranspiration, runoff, and the benefits of green infrastructure? Also, are there any NASA-related application case studies that demonstrate this type of integrated analysis?
Okay, yeah, so another pretty loaded question. What I've written down here are just some examples that came to the top of my head. The EcoStress, we do provide a standard evapotranspiration product, which is derived from hydrological models that we actually run at JPL. I won't get into the details of those models, but those standard data products are available, and they are in fact fed directly into a lot of watershed water balance models as the latent heat term. And you can do your own literature search to find those studies. In terms of the benefits of green infrastructure for the LA 28 Olympics, we've actually been working with the LA committee and also other groups from USC, UCLA, as part of the Shade LA organization, to see if we can help use EcoStress LST data specifically to try and quantify which areas would be optimal for implementing, for example, heat mitigation measures, so planting more trees, implementing more shade structures, and so forth. And so we've been working on this machine learning model. It's actually a double causal machine learning model that integrates EcoStress LST with a number of other different variables to try and estimate what the cooling benefits are or would be of planting more trees in the city. So that is work that is ongoing. It's actually going to be sponsored by NASA pretty soon, and we're going to be working more closely with the city. Two really good papers that look at the urban biosphere influence, specifically on urban heat and carbon uptake in general in the urban environments focused on Los Angeles, were these two papers right here, written by two JPLers. I would encourage you to go and look in more detail at those papers for what is done there.
With that, I would like to again thank you, Dr. Glenn Hulley, for joining us for this ARSET training series, and thank you to all of our participants for joining us. And we will again be posting all course training materials and the Q&A document within a week of this training.